All right, I think we're live. So, hey everyone, good morning, good afternoon, or good evening, depending on where you are in the world. Thanks so much for joining us today for this live workshop. Today, Nithin Jois will be returning as our presenter. He's one of the instructors on tons of courses on AppSecEngineer, so you can see more of him over there. In this live session, he'll be showing you how to attack AWS Elastic Kubernetes Service, or EKS, through a series of hands-on labs which you can follow along and do too. Feel free to ask questions during the stream, and we'll do our best to answer as many of them as possible. Anyway, the floor is yours, Nitin.
Hey, Anish, thanks so much, man. First of all, super excited to be back, folks. I think last month it was conducted by, I think, Sharath and Abhay. I'm back and I'm super excited to be conducting this Attacking AWS EKS workshop. Now, quickly, I'm going to go ahead and share my screen. Bear with me for 1 second. All right. So again, welcome everybody to Attacking AWS Elastic Kubernetes Service. We're going to quickly start off with the content, and then we're also going to have a hands-on lab where you're going to be creating your own Kubernetes cluster on a sandboxed AWS environment. So even if you do not have your own AWS account, that's totally fine. You will be using our lab portal to go ahead and create a sandbox AWS environment. You'll be launching or creating your own Kubernetes cluster, and then you're going to go ahead and attack it as well. Right. So going to quickly start off with some of the learning objectives that I have in mind for this entire session. And then we're going to move on, learn a little bit more about Kubernetes for the folks who are not very familiar with it. Right. So we're going to go learn about Kubernetes, learn about EKS more specifically, and some of the changes or the differences between a self-managed cluster, self-hosted cluster, and a managed cluster. And we're going to look at our attack surface, and then we're going to move on with our labs. So with that, let's quickly get started with our learning objectives for the session. Right. So first of all, we're going to have a high level overview of the entire Kubernetes architecture. Right. So if the Kubernetes architecture is something that you're not very familiar with, that is totally fine. We're going to quickly go ahead and explore the different components in a Kubernetes cluster, and this is going to be pretty important from an attacker's viewpoint, because you can go ahead and start attacking some of these components or services that are running as part of your Kubernetes cluster, right? So they can be potential attack vectors. So it's pretty important to go ahead and learn more about them. And once we are done learning a little bit more about the entire Kubernetes architecture, we're going to learn the difference between a self-hosted Kubernetes cluster and a managed Kubernetes cluster. Now, if you've used AppSecEngineer already, or if you've taken some of our courses either in a live training somewhere or on AppSecEngineer, typically the way we deliver this is specifically the Kubernetes training is we help you create or set up your own Kubernetes cluster from scratch, right? So this is mostly because we get a in-depth overview of the components and what is actually happening within that cluster. So we're going to be looking at self-hosted cluster and a managed Kubernetes cluster, and some of the differences, the pros and cons, and so on. Now, once we're done with that, we're going to be focusing on AWS EKS. And it's important to know or understand the responsibility model, right? So we need to understand what we're going to be responsible for as end users or as end customers. At the same time, we're also going to have a clear overview of what AWS is going to be responsible for as well. Now, finally, once we're done with the responsibility model, we're then going to move on to understanding the attack surface for AWS EKS. Right, so we're going to look at the various attack vectors where things can potentially go wrong, where an attacker can go ahead and try to leverage misconfigurations to try and gain access to the entire Kubernetes cluster. And finally, we're going to go ahead and run a fairly simple lab where we're going to go ahead, deploy our own Kubernetes cluster on AWS. We're going to deploy our application on top of it. And then we're going to learn how we can go ahead and compromise this application and eventually compromise the cluster, the AWS infrastructure, and more. Right. So with that, let's go ahead and quickly get started with a high-level overview of the entire Kubernetes architecture. So what you have on your screen, right? So the image that is currently present on the screen gives you a high-level overview of how Kubernetes actually works. Now, typically, whenever you're going to be communicating with a Kubernetes cluster, as a developer or as an operator or somebody from the DevOps team or from the security team, you're going to be talking to the API server, right? So as an end user, you're typically going to be talking to the API server, and there are two ways to go ahead and communicate with the Kubernetes cluster. You can either do it using a user interface or something like a Kubernetes dashboard, or the other way is to use a CLI, that is kubectl or kubectl. Now, when you communicate with the API server, that internally goes ahead and communicates with multiple other components as well. Now, one of the first component that it's going to go ahead and communicate with is the scheduler. Now, typically, when you're going to be using a Kubernetes cluster, you'll want to deploy a number of pods across your entire Kubernetes cluster, right? So the scheduler is going to be responsible for scheduling or picking the node where it needs to go ahead and run your particular pod or your container, right? So that is what the scheduler is going to be responsible for. So let's take an example and say we have a Kubernetes cluster with 5 nodes, right? So the scheduler is going to look at node number 1, 2, 3, 4, 5, and then it's going to determine which node it needs to go ahead and deploy your container on, and it's going to go ahead and launch your pod there. The next component that we have is the HCD. Now, the HCD is the entire data store for your Kubernetes cluster, right? So HCD is the key value data store where all of your configurations are going to be stored, right? So HCD is essentially going to be the data store for all the configurations, all the changes on your Kubernetes cluster. Then we have the controller manager, and the controller manager is actually responsible for a bunch of things, right? So it's going to be controlling the number of nodes on your Kubernetes cluster, right? So for example, let's assume that node number 3 goes down for some reason, right? So that particular server crashes and it goes down. Now the controller manager is going to go ahead and essentially see that node number 3 is down, and if necessary, it's going to go ahead and spin up a new node as well. So it can behave as the entire resurrection process as well. Then it's also responsible for something known as the replication controller, or handling the number of replicas of your application deployment on your Kubernetes cluster. So if you want your application to scale, and what you would typically do is you would create multiple replicas of your application within the Kubernetes cluster and have it load balanced. And that is going to be controlled by the controller manager as well. Now, if you're going to be using a managed Kubernetes cluster, right? So whether it's going to be EKS or GKE or even Azure Kubernetes Service, there is going to be an additional component that is as part of the controller manager known as the cloud controller manager. Now, this particular component facilitates the communication between your Kubernetes cluster and all the other services that are offered by the service provider, right? So for example, let's say if you want to go ahead and communicate with something like KMS or S3 or some other particular component, all of that is going to be managed by the cloud manager, right? So it's going to handle the credential provision, it's going to take care of your volumes and so on. So all of these components, that is the API server, the controller manager, the cloud controller manager, or the scheduler and etcd, all of these together are known as a control plane. Now, typically, whenever you're going to be using a managed Kubernetes cluster like EKS, you are not going to have access to any of these components, right? So all of these components are going to be managed by the service provider. In our case, they are going to be managed by AWS. If you have your own self-hosted Kubernetes cluster, on the other hand, you are going to be able to go ahead and essentially modify the configurations, make changes if you want, and so on. So those are all the components in the entire control plane. Now let's quickly look at some of the components inside every single node, and then we can move on further from there. Now inside every single node, there is going to be a component called the kubelet. Now the kubelet is essentially like a Kubernetes agent that's going to be running on every every single node that is part of your Kubernetes cluster, right? So the kubelet is going to be responsible for essentially executing the commands that you ask it to execute. So if you say, go ahead and create a pod, for example, the kubelet is going to be responsible for going ahead and spinning up your pod on a given node. The C advisor or the metric server is responsible for collecting the metrics of the container and of the node or the server and feeding it back to the API server and eventually to the scheduler as well, right? So if, let's take an example, right? So let's say node number 2, a bunch of resources are being used and it's almost maxed out. So next time when you ask your Kubernetes cluster to create a pod, the scheduler is going to look at node number 2. It's going to understand that, hey, you know what, it does not have a bunch of free resources, so I'm going to go ahead and deploy it on a different node, right? So that is the role of the C advisor or the metric server. The next one we have is the kube proxy. Now, the kube proxy is essentially going to be responsible for networking within that particular node, right? So if pod number 1 needs to communicate with pod number 4, it's going to happen via the kube proxy, right? So pod to pod communication inside a particular node, all of that is going to be facilitated through the kube proxy. And finally, we have a pod. So a pod can either be a single container or a combination of multiple containers that are going to be running on your cluster. And the plugin network, this is going to be responsible for the entire OLA network for all of your nodes on your Kubernetes cluster, right? So let's take an example where pod number 1 on node 1 needs to communicate with pod number 4 on node 3, right? So that can essentially happen through the plugin network. So since we're going to be concentrating a little bit more on EKS and managed Kubernetes clusters, let's look at some of the components inside the Cloud Controller Manager itself. Now, excuse me, sorry, 1 second. Okay, so inside a Cloud Manager components, right? So these are some of the components inside a AWS Cloud Manager. The first one is going to be the Cloud Controller Manager. Now, this is going to be responsible for creating and updating things like the load balancer, right? So if you want to go ahead and expose your application to the public internet, you'll have to create a service. And if you want to go ahead and create something like a load balancer service, that is going to be facilitated through the Cloud Controller Manager. And it's also responsible for the node lifecycle management as well. The next one is going to be the AWS Credential Provider. Now, AWS Credential Provider is going to be important to provide credentials to pull images from a private registry, right? So typically when you're going to be running your Kubernetes cluster, all of your Docker images are going to be private inside Elastic Container Registry or ECR. Now, the way you would do it is you would go ahead and essentially given the credentials and AWS, your EKS cluster is going to be able to pull in the private images from ECR with the help of AWS Credential Provider. And finally, if you will want persistent storage for some of your applications on your Kubernetes cluster, you will need volumes, right? So the volume plugin is going to be responsible for provisioning storage objects in AWS. And it's currently in maintenance mode, but it's going to be replaced by EBS CSI driver very soon. So with that, let's look at some of the Cloud Controller Manager functions. Right, so the Cloud Controller Manager, first of all, is going to be responsible for controlling the number of nodes on your Kubernetes cluster. It's going to be responsible for the routes. And finally, it's also going to be responsible for services as well. So let's try and understand some of these in a lot more detail. So when you talk about the node controller, right, so it's going to be responsible for updating node objects when a new node is created. So let's say you want to go ahead and scale your Kubernetes cluster and add in a couple of more nodes if necessary, right? So in such a situation, the node controller is going to be responsible for updating all of those node objects. The next one is going to be route controller. Now the route controller is responsible, as the name suggests, for configuring the routes, right? So that the containers within the Kubernetes cluster can go ahead and communicate easily. And finally, the last one is going to be the service controller. And this is typically going to be used to interact with the cloud provider to provide, for example, load balancer, IP address allocation, network packet filtering, uh, health checks, and so on. Right. So all of these things are going to be handled by the service controller. So these are some of the key functions or components in a managed Kubernetes service. So with that, let's quickly understand the difference between a self-hosted Kubernetes cluster and a managed Kubernetes cluster. Now, when you look at a self-hosted Kubernetes cluster, now since you are going to be the one who's going to be creating the entire cluster from scratch on a server that you have complete control over, you are going to have more control, right? So if you want to go ahead and make changes to the API server, you can go ahead and do that. If you want to change the way etcd, for example, is configured, you will have the permissions to go ahead and do that as well. So on a self-hosted Kubernetes cluster, you're going to have more control of all the components within the control plane that we previously spoke about. One of the key disadvantages of a self-hosted Kubernetes cluster is that it is hard to scale, right? So every time you want to go ahead and add a node to your Kubernetes cluster, you're going to have to leverage the kube admin, get the token, add a new server to the Kubernetes cluster, and so on. So it's fairly difficult to go ahead and automate this entire process. And if you want to auto scale and do all of those things, if you want to scale up or scale down, it's going to be pretty complex to go ahead and do it on a self-hosted Kubernetes cluster. Additionally, it's also going to be a little difficult to maintain, right? So you're going to have to constantly keep track of some of the zero-day security issues that pop up for some of the components in Kubernetes. Every time there's an update that's released, you're going to have to go ahead and update your Kubernetes cluster. If there are changes made to the API version, you're going to have to go ahead and maintain that, which can be pretty tricky, right? So all of these bottlenecks, or there are multiple friction points when you're going to go ahead and essentially run your own Kubernetes cluster. Then one more option or an advantage is you have more options to deploy the cluster, right? So all you need to do is spin up a server or a virtual machine, install kube admin on top of it, and you're off to the races, right? So you can go ahead and spin up your own Kubernetes cluster. But again, you will have to keep in mind some of the security considerations while you're doing that, right? So you should essentially make sure that some of the components are not exposed to the public internet, for example, like etcd, because if it's going to be exposed and if an attacker can essentially manage to gain access to all of the configurations stored within etcd, it can be pretty dangerous, right? So which is why keeping security in mind is going to be critical. Also, managing a self-hosted Kubernetes cluster does require more expertise, because we saw the number of components that are part of of an entire Kubernetes cluster, right? So you're going to have to understand the key configurations into each of these components, which are going to be part of your Kubernetes cluster, and you're going to have to understand them in a way where you're going to be responsible for fixing any misconfigurations. If there is a new patch released, or if there's a new configuration that you need to go ahead and implement, you are going to have to do that as well. And this ends up consuming a lot of time when it comes to configuring your entire Kubernetes cluster. But at the same time, it's going to end up probably costing you a little less, depending on the scale that you're running it at. Now, when you look at a managed Kubernetes cluster, on the other hand, you have less control, right? So, for example, you're not going to be able to essentially modify the way the Kube API server is configured, or you're not going to be able to modify the way etcd has been configured. All of those components, which are part of the control plane, you will not have access to, which in one way makes it more secure. But at the same time, you will not have the ability or the flexibility to go ahead and make changes. But at the same time, this is extremely easy to scale and maintain, right? So if you want to just auto scale it, all you need to do is enable auto scale, and it's going to go ahead and, as and when the load on your Kubernetes cluster increases, it's going to start adding more nodes as part of your entire Kubernetes cluster. The one of the disadvantages is less options to deploy the configuration, right? So there are only a handful of managed Kubernetes clusters that are available, and the big ones are going to be EKS, your GKE, and AKS. That's by AWS, Google, and Azure. But at the same time, DigitalOcean, Linode, CEVO, there are multiple other options that you can go ahead and potentially look into to go ahead and deploy your Kubernetes cluster. Now, this does not necessarily require as much expertise as you would need when you're managing your own Kubernetes cluster, because you do not have to worry about the low hanging fruits, right? So you don't have to worry about some of the potential security issues that pop up, which are fairly easy to fix and go ahead and configure, because all of those are typically going to be handled by the service provider themselves. And it also takes very little time to go ahead and configure your own Kubernetes cluster, right? So it typically takes less than 15 to 20 minutes, and you can have your own Kubernetes cluster spun up. But at the same time, it's going to end up costing more. But one key concern that we're obviously going to be looking at in a lot more detail is security. Now, depending on the way you go ahead and configure it, managed Kubernetes cluster can obviously be a little bit more secure, because of certain class of attacks are not going to be available, right? So if you want to go ahead, and typically an attacker would try and compromise the API server or the controller manager or the HCD, or those certain class of flaws where you're attacking the Kubernetes components directly, that is not going to be possible most of the time on a managed Kubernetes cluster. On a self-hosted cluster, on the other hand, you are going to be responsible for it. So with that, let's actually look at the shared responsibility model for different AWS Kubernetes services. So here we have a representation of a self-hosted Kubernetes cluster. Now, on a self-hosted Kubernetes cluster, as an end user, you're going to be responsible for the control plane, all of the components within the control plane. You're going to be responsible for the data plane, which is going to be the nodes and the networking aspects. You're going to be responsible for that, and you're going to be responsible for the application that you're going to be deploying on your Kubernetes cluster as well, right? So on a self-hosted Kubernetes cluster, you're going to be responsible for the entire thing. Now, on EKS, on the other hand, you will not have access to the control plane like we spoke about previously. But the security of the entire networking aspect, the nodes, all of that is going to be handled by you. So you're still going to be responsible for the data plane, the way your VPC is configured, the application that you're going to be running, how you're going to be running it, and how it's configured. All of those things you are still going to be responsible for on EKS. Now, if you use AWS Kubernetes with Fargate, on the other hand, your node components are going to be managed as well, right? So you do not have to worry about the node where your container or your pod is going to be running. AWS is going to be responsible for the control plane, the data plane, and the only thing that you're going to be responsible for is your application, right? So if your application is inherently going to be vulnerable, right? So if it has a couple of vulnerabilities in them, that would still mean that your entire Kubernetes cluster can be attacked. So let's look at a slightly different representation of this and get an in-depth overview of some of the things that we are going to be responsible for and some of the things that AWS is going to be responsible for. So in our example right here, we have self-managed workers and EKS Fargate, right? So in self-managed workers, AWS is going to be responsible for the HCD, the API server, the controller manager, the scheduler, all of those components which are part of the Kubernetes control plane. But on the other hand, we are still going to be responsible for the container images that we are going to be running on our Kubernetes cluster. We're going to be responsible for the customer data. We're going to be responsible for the cluster configuration and how we go ahead and essentially configure the nodes on the cluster, the networking on the cluster. We're going to be responsible for it. Any add-ons, any network policies, all of those things we are still going to be responsible for. But if you're using EKS Fargate, on the other hand, your worker node scaling, right? So if you want to go ahead and scale your nodes, you don't have to worry about that, right? So AWS is automatically going to go ahead and handle it for you. You also do not have to worry about the operating system or of the node wherever your pods are going to be running. You don't have to worry about the kubelet within those nodes where your pods are going to be running, and you don't have to worry about the underlying AMI configuration for the server or the node where your pods are going to be running, right? So all of those things, along with the entire control plane, is going to be the responsibility of AWS, right? So in case of cloud providers in general, uh, typically you will not have access to the control plane. However, things like role-based access control and essentially setting up your own Kubernetes cluster in a secure way, that is still going to be your responsibility. So with that, let's quickly look at the entire attack surface of EKS, and we're going to quickly move on. Essentially set up our own Kubernetes cluster on EKS, and we're going to get started with the lab. So the first one is going to be misconfigured IAM roles, right? So misconfigured IAM roles is actually that certain class of flaws which is going to be there across multiple AWS services, right? So whether you're using EKS or EC2 or any other service, if your identity and access management is not configured properly, this can be a huge attack vector, and the potential damage it can cause is can be pretty considerable as well. So when it comes to EKS more specifically, we speak about giving excessive permission either to the nodes or to the service accounts, and which can potentially lead to privilege escalation. The next one is going to be a vulnerable application, right? So a vulnerable application can typically lead to something like a reverse shell, where you can get shell access to the application that is vulnerable, or you can try and gain access to sensitive information through other attacks. And we're going to be looking at one of those attacks as part of our lab as well. The next one is going to be outdated packages or kernels in the worker node. Now, if the kernel itself is outdated, or if it's vulnerable, then an attacker can try and gain access to the node, and by gaining access to the node, they can try and gain access to the entire Kubernetes cluster as well. Because again, remember, kubelet is going to be running on the node, and multiple other components are going to be present on the node, right? So from by gaining access to the node, it is possible to try and gain access to the entire Kubernetes cluster. And finally, we have the misconfigured network access. So, for example, if we have an open firewall or misconfigured NACLs, this can lead to accessing applications which might be internal and which might end up leaking some amount of sensitive information as well. Right. So, on a very high level, these are some of the attack surface in a typical Elastic Kubernetes service. Now, one of the most common forms of attacks in actually AWS that lead to privilege escalation is compromising the service account token or the security token service. And this can be a whole lot worse if the IAM roles that are attached are poorly configured. For example, if you've given wildcards or if you've given access to resources that this role typically does not need to have access to, this can lead to potential privilege escalation. And from a simple application vulnerability or an application flaw, an attacker can gain access to the Kubernetes cluster, and from there they can actually take over the entire infrastructure as well, right? So this is one of the key security concerns when it comes to attacking a managed Kubernetes cluster. Now, typically in a self-hosted cluster, you would gain access to the entire Kubernetes cluster, and that's bad enough. But in a managed Kubernetes service, you can gain access to the cluster, and from there you can go ahead and leverage a token or a service account token or a security token service that's going to be available, and through that you can start compromising the entire infrastructure as well, right? So the overall damage that can be caused is considerably higher in a managed Kubernetes service. So typically the attacker would compromise a compute resource, and from there they would go ahead and fetch the token, and through that token they would go ahead and start compromising other resources as well, Right. So let's quickly take a look at a example, and we're going to go ahead and move on to a lab. So here we have an example where we have a EC2 server or an EC2 instance. And obviously this EC2 instance has a instance profile attached to it. Now, typically for any EC2 instance, there is going to be a role attached to it. And if you want to fetch the key ID, the secret token, and access key for the role that is attached to the EC2 server, the way you typically go about fetching access is by contacting the metadata endpoint. Now on AWS, especially for EC2, the metadata endpoint is going to be on the IP address 169.254.169.254. So if it's loosely scoped or if it's not configured well, you can go ahead, access it, fetch the essentially the access ID, access key ID, the secret token for the role that is attached to the EC2 server, and start using that and start gaining access to other services, right? So for example, let's say the EC2 role that is attached has access to DynamoDB tables or S3 servers or KMS or SSM. You can start communicating with all of those services with AWS CLI, and you can gain complete access to it. So when you look at the paths to AWS tokens or credentials, one way to go ahead and gain access to them is by disclosure, which might sometimes be a mistake, right? So we have come across examples where access key IDs and secret tokens have been committed to Git repositories and sometimes even public ones. Obviously this can be pretty dangerous. Now recently GitHub, I think just a few days ago, launched a new service that helps you scan for secrets on your GitHub repositories, which should ideally go ahead and reduce the attacks from stealing tokens from GitHub. But at the same time, it is still possible. The next way is going to be via either build scripts or via misconfigured CI services, right? So if your Jenkins is not well configured, or if itself is vulnerable, and you've configured Jenkins to communicate with your AWS infrastructure, if an attacker can manage to gain access to one of your CI services or your build scripts with hard-coded credentials, they can go ahead and start gaining access to the entire infrastructure as well. And finally, you have other communications through which it can be compromised. And if you're using AWS Amplify, and if that is misconfigured, your credential can be compromised through that as well. But on the other hand, if an attacker manages to compromise an application or or an operating system, they can go ahead and gain access to the tokens through metadata endpoints as well. Right. So if you're using EC2, 169.254, the IP address that I previously mentioned, you can essentially communicate with that particular metadata URL, and you're going to be able to access that. If you are using Elastic Beanstalk or EBS, that also has a different endpoint, which you can go ahead and leverage and essentially fetch the tokens. Similarly, for ECS or for Fargate containers, you can go ahead and all of these IP addresses are there in the official AWS docs. And I'm going to be showcasing them in the next slide as well. But you can talk to the metadata URL and essentially fetch the tokens and then go ahead and continue with the attack. And finally, for AWS Lambda, there is no endpoint, but all of the tokens are going to be stored as environment variables, and they're going to be available in plain text. So if you can go ahead and essentially print out the environment variables, you can steal the tokens from there and try and gain access to other resources as well. So when you look at some of the AWS compute services, for EC2, we have a metadata URL, and a typical remediation for this would be to upgrade it to IMDS v2. Again, if a user manages to gain shell access or reverse shell to the EC2 instance, it's still going to be hard, but at the same time, you can prevent a certain class of attacks. Similarly, for Elastic Beanstalk, we have 169.254.269.254. Again, the remediation for this would be to go ahead and upgrade it to IMDS v2. For Fargate, on the other hand, we have a different IP address for the metadata endpoint. And for Lambda, it's going to be environment variables. Now, again, this is not just for AWS, or it's not AWS specific only, right? So typically, Google Cloud is going to have its own separate metadata endpoint. I'm sure DigitalOcean has its own separate metadata endpoint. So does Azure as well, right? So all of these services are going to have these metadata endpoints through which you can essentially try and communicate with them, fetch tokens, and through that try and gain access to the entire infrastructure. So AWS metadata is it's a huge class of attacks that can happen on a typical AWS infrastructure. And typically speaking, a compromised pod can lead to the exposure of metadata because your pod is going to be within your Kubernetes cluster, and from the pod you're going to be able to gain access to the either the service account token or to the metadata URL. And using both of these things, you can leverage them to go ahead and escalate privileges within AWS. Now, typically, the token file that is going to be injected into a EKS pod is going to be in the part where run secrets, EKS, service account, and token. So by stealing or gaining access to this particular token, you can go ahead and start compromising the entire Kubernetes cluster, try and gain access to other resources, and eventually, if it has all the permissions necessary, you can go ahead and attack the entire Kubernetes cluster as well. Right. So with that, let's go ahead and get started with our lab. Now, in our lab, what I'm going to be doing is I'm going to be launching a intentionally vulnerable application. That's I'm going to go ahead and create my own or deploy my own intentionally vulnerable app on the Kubernetes cluster that I have set up. And this particular app is going to be vulnerable to a flaw called server-side request forgery. Now, typically, the way it would work is you're going to have your application, and this application is going to essentially have a form or a field where you can go ahead and enter data. Now, if it is vulnerable to something like server-side request forgery, which is typically due to a parsing functionality or a vulnerability in the parsing functionality, you can leverage that by giving it payloads and asking it to communicate with resources that are internal, right? So I can have it communicate either with the database or with localhost, or in our case, we can have it communicate with the metadata endpoint. And through that, we can try and start stealing the AWS tokens and try and gain access to the entire infrastructure, right? So typically your URIs would include HTTP or HTTPS or file or SSH or Gopher. So if the parsing functionality is vulnerable, then your application might potentially be vulnerable to server-side request forgery. So with that, let's go ahead and get started with the lab. Again, uh, if you want access to the lab, you will have to go ahead and sign up on AppSecEngineer. I'm sure Anish can go ahead and share the link on our Discord server. And if you have a subscription already, that's great. You can go ahead and you should see a course called Attacking AWS EKS there, and you can go ahead and use that. All right. So with that, let's go ahead and get started. So this is the lab that I have right here. Now, one of the things that you get if you're going to be using AppSecEngineer is you don't have to worry about bringing your own AWS environments or your own AWS account, because we're going to be deploying a bunch of misconfigured applications or intentionally vulnerable applications on our AWS infrastructure, right? So, which is why what we do is we go ahead and we have AppSecEngineer CTL or ASC CTL, through which you can go ahead and provision an account on our AWS, which is going to be a sandboxed environment, right? So each and every one of you, you're going to go ahead and get access to your own AWS account. So you don't have to have your own AWS account and worry about the billing and whatnot. So I'm quickly going to run you through some of the steps that I have run right here. Now, setting up a Kubernetes cluster does take a while, right? So it usually takes anywhere between 10 to 15 minutes. So before we got started, instead of us wasting our time, I've gone ahead and run step 1 to step 4 already. Right. So now if you want to go ahead and provision and run your own lab, that's totally cool. You're more than welcome to do so. But I have gone ahead and run step 1 to step 4, Now let's quickly go through that and see what's happened. So I started off by running ACCTL init AWS. Now this is going to go ahead and initialize a sandboxed environment for me, and it's going to write credentials, and into the credentials file, it's going to write my AWS config, and finally all of my credentials, it's going to be available in aws-creds.txt. So again, this is also going to have a username and a password field. So if you want UI access to your AWS account that you're going to get through this, you can go ahead and access it through that as well. So finally, once we're done with that, in our step, we're going to be using Terraform to go ahead and create our Kubernetes cluster. So I'm going to navigate to the AC EKS SSRF directory, and then I'm going to initialize Terraform to install all of the plugins, right? So this is going to install all of the necessary plugins. And finally, once I'm done with that, I'm going to go ahead and run Terraform apply auto approve, right? So this is going to go ahead and start creating my EKS cluster on my AWS account that I have right here. So this is going to go ahead and create my entire EKS cluster. It's going to take a while. Typically, it's going to tell you about all of the resources that are currently being created. And you can see that there is a public route that's available right here. Public subnet is available. So we are going to be able to access our Kubernetes cluster from a public IP address. But one more thing that I would like to point out is I'm also additionally adding a S3 bucket. I'm going to be adding or uploading a file to this particular S3 bucket. And the file that I'm going to be uploading is going to be credit card numbers, right? So again, this is just an example where I'm going to go ahead, store credit card information on our S3 bucket, which our Kubernetes cluster is going to be using. And by compromising the application, we're going to try and see if we can gain access to uh, other resources within AWS through the tokens that we steal. So all of this is going to take a while. So as you can see right here, it's taken approximately 10 minutes and an additional 2.5 to 3 minutes to go ahead and create my entire EKS setup. And once it's done, as part of the output, it's going to give us the cluster name, which is randomly generated. Then it's going to give us the worker node role name. And we also have an S3 bucket, right? So our S3 bucket is going to be this one right here, which is randomly generated again. And finally, the endpoint where our Kubernetes cluster is going to be running, right? So this is essentially going to be the API server that we can typically communicate with. So that what I'm going to do right now is I'm going to head over to step 5, right? So all you need to do on our platform is come back right here, copy, or if you want to type it out, you can do that as well. I'm just going to copy it and paste my command right here. So in our lab, we're going to be deploying this on US West 2, right? So this is where we're going to be running it. And I'm going to say update kube config. And the cluster name is going to be this one right here, right? So I'm going to essentially fetch the cluster name as a variable, and I'm going to update my kube config. Now this should go ahead and create my .kube config file right here, right? So I'm going to be using kubectl, and using this, I'm going to be able to authenticate and authorize myself on the Kubernetes cluster that we have set up. So with that, we can start running our kubectl commands, right? So the first thing I'm going to do is I'm going to say kubectl get nodes. I'm quickly going to clear the screen so that it's visible. Type it right. All right. So I'm going to say kubectl get nodes, and this should tell us the number of nodes that essentially belong to our Kubernetes cluster. And in our example, we currently, it looks like we have 2 separate nodes that are there. And it's also going to tell you the EKS version that they are going to be running on. So like I previously mentioned, I essentially created this cluster before we got started with the live stream. So it's been approximately 70 minutes, but you can go ahead and spin up your nodes by running the commands. The next thing I need to do is obviously deploy my application, right? So let's head over to vulnerable deployment or vuldep. And this is the application that we're going to be deploying, right? So we have on our V45 Docker Hub, we have a EKS attack privilege escalation. We're going to go ahead and essentially create this particular deployment, which is going to create two separate replicas for us. And if I think this is going to be on the default namespace, right? So I've not mentioned any namespace right here. So it's going to go ahead and it's going to create this on the default namespace, which again is not ideally recommended. So if I say kubectl get deployment, it should tell us that our deployment is still being created. And similarly, I can do kubectl get pods to fetch all the pods that are currently running. Now, since it's two separate replicas, I expect two pods to be available, and it is, right? So I can see that there are two separate pods that are running. Now, obviously, this particular application is intentionally vulnerable, and I do not want to expose it to the public internet by default, right? So, since this is a live stream after all, but what I'm going to do is I'm going to export it, and I'm going to leverage the port forward to access our particular application, right? So, our application, I'm just going to export the name of the pod that is running. I'm going to fetch the server IP, and using my lab instance server IP, I should be able to access the application that is running on my Kubernetes cluster. So I'm just going to say kubectl get pods, and I'm going to paste in my command that is going to export the application name, right? So if I try and echo it, there is a little bit of a lag for some reason, forgive me. All right, so I can see that it's essentially using my first pod, right? So I'm going to be essentially talking to my first pod and communicating with it. The next thing I want to do is I'm going to fetch my server IP, right? So this is going to be IP of my lab instance right here. So this is going to be on. Obviously, you folks are going to have your own servers and your own IP addresses, but this is the IP that my lab instance is currently running on. And finally, I'm going to use the port forward functionality of kubectl to access my application, which is running inside this pod. So I can access this particular IP address and head over to port 5000. And I can see that, hey, you know what, it requires an email field for me to go ahead and subscribe, right? So if I can go ahead and enter an email, for example, appsecengineer@gmail.com, which probably does not exist, right? So I can go ahead and subscribe it and it should work. And it's giving me an error saying HTML, the document has been moved. And this is interesting, right? So I just gave it an email address. It's communicating with somewhere and it's giving me a bunch of information with header text and it's telling me 301 moved. And finally, it's telling me a href of google.com/gmail, right? So there's something clearly wrong with this particular field that we have right here. So what we can try and do is we can try and leverage this and see if we can communicate with the metadata endpoint. So what I'm going to do next is I'm going to try and access 169.254, 169.254 latest metadata IAM. And I'm going to see if I should be able to access that. If I click on subscribe, it's going to tell me that, hey, there's something in info/security credentials. So let's try and dig a little further, right? So let's try and see what is actually there inside this particular security credentials. Now, inside the security credentials, there seems to be some name or some randomly generated role that's currently available. So what I'm going to try and do right now is I'm going to try and fetch the particular token that belongs to this particular role that we have right here. So I'm going to copy this entire line, come back here, paste it, and I'm going to have to replace my role name in documentation with the actual role name that I have right here. And if I hit on subscribe, it's going to give me the access key ID, the secret key, and the token. So I'm just going to copy all of this, come back to my lab server. I'm just going to create a new Scratch file. And I'm going to go ahead and paste it here, right? So if it's created successfully, I'm going to go ahead and essentially paste my all the things that I just stole, the tokens I stole. I'm going to go ahead and paste them right here. So with that, I'm going to open up a new terminal right now, right? So if you want to open up a new terminal, all you need to do is click on the terminal right here and then select new terminal. And I'm going to start using these credentials that I have right here, which is going to be the access key ID, the secret access key, and the token. I'm going to go ahead and essentially use all of this information, and I'm going to essentially compromise my AWS infra. So what I'm going to have to start doing is first I'm going to export the access key ID. So I'm going to copy this right here, come back, paste it, and actually fetch the value of access key ID. Right, so by exporting this, right, so it's not going to use my .aws config. So I have my on my particular server right here, I have credentials that are stored already. But if I do not want to use these credentials, and if I want to go ahead and use these instead, I can just store all of the access key, the token, and the ID as environment variables. And if I run AWS on this particular environment or on this terminal tab, it's going to go ahead and use the credentials that I give it as an environment variable. Now, similarly, I'm going to go ahead and give it the access key as well. So this is going to be my access key, which I'm going to go ahead and copy. And finally, I need the token as well. So I'm going to go ahead and copy my AWS session token. I'm going to copy this entire value that I have right here. All right. So with that, AWS on terminal one, which I'm going to just drag and drop right here. So that's it's easy. So here it's going to be configured to use the credentials that are available in the environment variables. So let's say if I just do sts get caller identity, it's going to give me this random user ID. But if you look at the role, it's going to be the assumed role of the and the node, right? So these are going to be the node credentials that we just ended up stealing. So that the first thing I'm going to try and do is see if I have access to AWS S3. Because remember, previously when we were setting this up, we had a sensitive file as part of our S3. So I'm just going to go ahead and say AWS S3 ls. And I can see that there is a bucket right here, which has a random name -SSRF. So I'm just going to go ahead and see if there is something within that particular S3 bucket. And looks like there is, right? So there seem to be credit card numbers within that. So what I'm going to do right now is I'm going to copy that entire txt file onto my server right here, and then let's try and look at the credit card numbers. So I'm just going to do this, and I'm going to copy this entire line right here. So I'm going to say steal the credit card numbers.txt and paste it on my particular lab instance right here as card numbers. Not sure why that didn't work. Maybe I'll just give it the same name. Right, so I'll go ahead and just give it probably the same name that I have right here. Maybe that is why it's happening. Or a dot. Let's try and see. Well, I'm doing an ls. Sorry about that. I should have done a copy command. My mistake. So instead of S3 ls, I should have done S3 copy, which is why it's like unknown options, which was kind of weird. Anyways, so I'm just going to go ahead and again follow the instructions, folks. I'm going to do CP, and that should give me my credit card numbers right here. And with that, I can go ahead and I have access to other resources apart from AKS as well, right? So I can go ahead and start. If I want access to EKS, I can potentially gain access to that. But if I want access to either KMS or S3 or any other resources that this particular role has access to, I can go ahead and fetch access to all of those resources as well, right? So which is why this it can be pretty dangerous, especially if you're going to have a vulnerable application or a misconfigured application running on your Kubernetes cluster. All right, so with that, we have come to the end of our lab slash demo. You are going to have access to this entire lab for, I think, the next 24 hours. If you're using a free trial, if you have a paid subscription already, you're going to continue having access to this, right? So again, if you're not on our Discord server already, it kind of gets pretty noisy in there. I would highly recommend you get in because there's a lot of information that is constantly being shared amongst us. So be sure to subscribe or get access to our Discord server. And if you have any questions, you can post it there as well.
Yep. Great. I think that's it for our live session today. So this video will continue to be available on YouTube, and as Nithin said, you can find the actual labs on our AppSecEngineer platform. And if you have any questions, please go ahead and join our Discord server. I've dropped the link in the description and in the comments. So we'll see you there. All right. See you next time. See you next month with another live session just like this. All right. Bye bye.
Bye, folks.